Good morning, good afternoon, good evening, everybody. My name is Kartik, one of the co-founders of ETH Global, and I'm super excited to welcome all of you to the final week of ETHOnline. This is a massive event, and all of you are watching this thing on ethglobal.tv. For today's summit, we will be also using this platform to make everything interactive. So if you have any questions for our speakers or any other comments or chats, or if you want to communicate some links to you, we'll be pasting them on the chat. So log in and say hi. And let's get right into it. ETHOnline is our flagship async event. And our mission here is to onboard thousands of developers into the Web3 ecosystem. We do this thing by running hackathons and summits, both in person and async. And coming to ETHOnline, we're already nearing 1,600 hackers from 91 different countries, from 26 unique time zones participating, and we're just 2 days away from the submission deadline. We've already seen over 300 projects come in. So it's going to be absolutely incredible to see what everybody submits in just 48 hours. But today we want to do our last summit for ETHOnline, and that's going to be all about scaling and everything that's happening in the world of helping scale blockchains. A very short and sweet summit for all of you. We're going to have just 3 talks. First up is going to be Keone talking about parallel EVM. Then we're going to have Uma talking about ZKVMs with SP1. And then we're going to have a panel where Mark Heinway from Optimism, Max, and Justin Drake are going to be talking about multiple concurrent proposers. So we're going to learn about all the advancements happening in these 3 categories. And without further ado, let's get started with our very first talk. So I'm going to bring on Keone here to talk about parallel EVM and let's get right into it. Welcome.
Hello, everyone. Great to be here. My name is Keone Han. I'm the co-founder and CEO at Monad Labs. I'll be talking about improvements that help introduce parallelism within the EVM, both at a slightly higher level in terms of introducing pipelining between consensus and execution, as well as the optimistic parallel execution algorithm that we've been working on here at Monad Labs. Let's get right into it. So I guess just to first to mention really briefly, Monad Labs is building Monad, a new fully Ethereum compatible blockchain, and introducing improvements that at all layers of the stack in order to um, prove out what's possible in an Ethereum like layer one blockchain. So I'll be talking very briefly about what that looks like from the user and developer perspective. And then I'll be getting into under the hood, the technology that delivers some of these performance characteristics. So Monad is a from scratch blockchain that preserves Ethereum's interfaces. So you can think of it as a puzzle piece that has the same shape as Ethereum, both from a bytecode perspective. So it's fully EVM equivalent layer one, as well as from an integration perspective with full Ethereum RPC compatibility. From the user perspective, this means that users get the best of both worlds between performance and decentralization. From a performance perspective, that has an implication on cost. So, for example, we expect that a typical transaction, such as a Uniswap V2 swap, which is about 100,000 gas, we expect to cost on the order of a tenth of a cent or less. That comes from high performance because when you have a service that could provide a lot of units of supply, then the supply demand curve ends up converging at a low price. In addition, Monad also is offering decentralization through hundreds of nodes participating in consensus and by preserving reasonable node requirements. So that's from the user perspective. We think this is why these are some important improvements to be proven out that will be beneficial to users. Additionally, from a developer perspective, Monad, this design is intended to give the best of both worlds for developers by offering the best of both worlds between performance and portability. So I already spoke a little bit about the fact that full Ethereum compatibility is preserved, meaning that any contract built for Ethereum could be ported over without any changes, without even recompilation, which has the benefit that one can tap into the existing network effects of using Solidity and the EVM. So for example, there's so many libraries that have already been built in Solidity. There's so many applications that already exist in Solidity. And through atomic composability, it means that new applications can compose on top of existing applications already and tap into that network effect. Again, from a developer perspective, there's portability in terms of EVM equivalents. In addition, the high performance means that gas is really cheap, so that as a developer, you can write code without being overly concerned about gas optimization. So that means you can write code in a more intuitive way without having to drop into Yule and write code that's really hard to understand. In addition, it's a lot easier to write a lot more defensive assertions because even though those assertions cost a little bit more gas, that gas is very cheap. So we think that this improvement is important for improving security because with greater by basically shifting the calculus between gas optimization and rigorousness and defensiveness, we can deliver the best of all worlds. So that's a bit about why some of these improvements we think are helpful from a developer perspective. So in addition to the benefits from a user perspective, there are also benefits from a developer perspective. Now I want to talk a little bit about some of the optimizations, including parallelization at the execution level as well as at the consensus level that help enable these properties. So just to mention really briefly, I think there are four major resources that any blockchain designer is ultimately conserving and trading off. And those are in order: network bandwidth, number 2, CPU throughput, number 3, state access, and number 4, state growth. These are fundamentally the constraints that ultimately limit the potential performance of a blockchain and that ultimately need to be utilized as efficiently as possible. But if we wanted to sort of juice up some of these parameters, then one could do this, for example, from a bandwidth perspective, just by raising the bandwidth requirements, or perhaps by putting all the nodes in the same geography. But if one were to do this, it would actually have a significant impact on decentralization, because then it'd be a lot harder for everyone to run a node, or in the case of geographic constraints, literally everyone only people in a certain geography could run a node. And similarly for state access, the easy way to address this problem is by raising the RAM requirements and keeping all the state in RAM. However, doing that would also have a massive impact on decentralization, because RAM is over 100x more expensive than SSD. So it's much, much, much more reasonable and efficient to store data on SSD. So these are sort of constraints, or these are resources that are being traded off. And we really want the whole premise of our team's goal is to get the most out of commodity hardware so that we can get really high performance while still preserving decentralization, which means for us, preserving reasonable RAM and bandwidth requirements, being fully geographically decentralized, and having hundreds of nodes participating in consensus. And in order to get this, we need new software architecture and a lot of low-level optimization rather than just throwing hardware at the problem. So this is the problem statement. How do we do that? We do that through 4 major architectural improvements, which I'll mention really briefly. Monad BFT is a performant consensus mechanism, asynchronous execution, parallel execution, and MonadDB, which is a new database for improving state access. And in this talk, I'm really going to focus on the last 3, which really are at the core of improving execution and introducing parallelism and pipelining to the execution process. So let's dive right into it. The first topic that let's talk about is asynchronous execution. So for background, most blockchains have interleaved execution and consensus within a block. So that means that nodes typically are executing and then running the consensus, or tasks that are related to the consensus process, and doing that in an interleaved fashion. And there's a really significant implication of this. The best analogy that I like to use is there's a popular movie known as called Limitless, and the premise of the movie is that humans only use 10% of their brain, and in the movie there's a guy who has this magical pill that he can take that allows him to use 100% of his brain. And so because it's a movie, of course, there's a period where things are going really awesome for him with his superpower, and then there's a period where there's a conflict, and then ultimately maybe the issue gets resolved. But it's kind of a cute idea, the idea of being able to use your whole brain instead of only a part of it. And the funny thing about interleaved execution is that exactly the same thing is happening here. Because consensus is very expensive because it involves cross the globe communication, it means that execution being interleaved with consensus gets squeezed into a very small fraction of the total block time as the time budget. So for context, in Ethereum right now, there's a 12-second block time, but roughly a compute budget of about 100 milliseconds, which is less than 1% of that 12 seconds. So this is pretty crazy, because in exactly the same way, blockchains are only being allowed to use 1% of their quote unquote brain to go and actually do execution work. So the goal, of course, of asynchronous execution is to go from using 1% to using 100%. And let's talk about how that is possible. So first, here's a diagram that kind of shows the interleaving between execution, which is in the dark blue rectangle, and the consensus, which is in the light blue rectangle. And so an interleaved execution, it's literally just kind of the simple logic of first execute, then come to consensus, then execute again, then come to consensus, and so on. And so here's a schematic that shows that relationship of the work being done for those blocks as a function of time, where time is on the x-axis and blocks is on the y-axis. So asynchronous execution basically splits these two components apart and has nodes only come to consensus. And then, so for example, what will happen is first consensus will occur over block number 1. Then two things will happen in parallel in two separate swim lanes, which are executing that block number 1 and coming to consensus about block number 2. So it's a pretty simple idea, just moving the execution out of the hot path of consensus into a separate swim lane and proceeding with that execution as soon as consensus is completed and in parallel to consensus on the next block. So if we just kind of draw this out a little bit more, this is what it looks like. And then replicating the diagram, this time with asynchronous execution, we see how things have changed. And you could see that they haven't changed by that much so far. They've changed a little bit in that we can start doing consensus on block 2 before execution on block 1 is has completed, and do these in parallel, which is a little bit of a time savings as indicated here. You could see that the blocks in the bottom part are starting a little bit earlier, but it's still a pretty small effect. But let's talk about what this enables now. So just to blow this chart up a little bit more, again, consensus is represented as the light blue rectangle and execution is represented as the dark blue rectangle. And the cool thing here is that now that execution has moved out of the hot path of consensus, we can actually raise the total amount of work being done in the execution loop by a substantial amount. And in fact, we can use in expectation the full block time as opposed to only a small fraction of it. So this means that we just have more time for execution, so we just have more time for more transactions to happen in each block. So that's it. It's actually a very simple concept. And it's exciting to see the idea of asynchronous execution starting to proliferate through the Ethereum and blockchain community as time goes on. There's some discussions in different research circles going on at this point, and on ETH research discussion forum. Just a couple things to point out as implications. One is that every node is now computing execution results independently, and separately, it also means that nodes are coming to consensus with a slightly delayed view of state. And there's special logic to kind of handle the implications of this, which are outside of the scope of this talk. But at the end of the day, this subtle change in how consensus and execution relate to each other massively raises the budget for execution. All right. So the next thing I'd like to talk about is parallel execution. And just to really briefly describe it, in Ethereum and most other blockchains, transactions are linearly ordered and they're serially executed. And in Monad, what we'd like to do is continue to have transactions be linearly ordered, but do the work in parallel while still achieving the same end result as if those transactions had been just executed one after the time. So in other words, we're hoping to work smarter rather than harder and get more work done by introducing parallelism. So 4 key points to understand about optimistic parallel execution. The first one is that it assumes in the parallel processing of transactions that all of those transactions are starting from the same view of the world. And just to point out one quick thing, optimistic here is totally different from what people mean when they talk about optimistic rollup. So even though it's the same word, it's a totally different concept. They're not related at all. Again, optimistic execution means that that transactions are being executed in parallel, assuming optimistically that they're starting from the same starting point. Okay, second thing to know about optimistic parallel execution is that it generates a bunch of pending results, one for each transaction, which are basically bookkeeping that's keeping track of any of the inputs and outputs for that transaction. When I say inputs, I mean storage slots that were read in, and when I say outputs, I mean storage slots that were mutated. So basically for all of those transactions that were executed in parallel, we're generating pending results that are these bookkeeping units. And then the third thing to know is that those pending results are then stepped through in the original ordering of transactions and committed in that order. And lastly, as we're stepping through and trying to commit each of those pending results, we're checking the inputs to make sure that they're still valid and re-executing any transaction whose inputs have since been invalidated. All right. So I think the easiest way to really understand optimistic parallel execution is just to go through an example. So let's say that at the start of the block, we have three actors, myself, Alice, and Bob. And let's assume that I start with 1,000 USDC in my account, and Alice starts with 0, and Bob starts with 300. And then let's imagine that there's 4 transactions that are in the block. The first one of which is me sending Alice 100 USDC. The second of which is some unrelated transaction. And the third of which is me sending Bob 100 USDC. So in this example, what we would expect to get at the end of this list of transactions is that my account ends with 800 USDC because I spent 100 USDC twice, and the Alice ends with 100 USDC, and Bob ends with 400 USDC. So let's now look at what happens when we do optimistic parallel execution. So as I mentioned before, optimistic parallel execution means that many transactions are being run in parallel, assuming basically the same starting point. So in particular, transaction number 1, when it's executed, is going to generate inputs of my USDC account and Alice's USDC account, of mine at 1,000 and Alice's at 0. And transaction number 3 is going to generate inputs of my account at 1,000 and Bob's at 300. And then, of course, the outputs are just the result, assuming those inputs. So transaction 1 will end with me having 900 USDC and Alice having 100. And transaction 3, again, when executed optimistically in parallel, will end with me having 900 and Bob having 400. So, when looking at this, we can already see that there's something that's going to be wrong, because transaction 3, as optimistically executed, it actually has an error. And we're going to notice that as we commit these pending results and deal with this issue when this happens. So first of all, we take pending result number 1 and we check its inputs. And since its inputs all match the previous state of the world, we just commit this transaction. In committing this, we commit this pending result. In the process of committing this pending result, we thus mutate the committed state. So now the committed state has me at 900 USDC, Alice at 100, and Bob at 300. Then we go to pending result number 2, which, since it was totally unrelated, doesn't have a conflict. And then we go to transaction number 3, and at this point, we're checking the inputs on pending result number 3, and we notice that pending result number 3 had my account at 1,000, but the committed state is now 900. So this is actually a conflict. So when we detect this conflict, we now will immediately re-execute this transaction. It must be re-executed. No other pending results can be committed until this gets re-executed. But when we re-execute, now we start with inputs of 900 and 300 and end with inputs of 800 and 400. And so at this point, this pending result is correct as well, and we can keep going. So that was kind of a simple example, but it really shows that the optimistic parallel execution algorithm is not rocket science. It's actually very easy to understand. It's doing the intuitive thing, and it's just doing bookkeeping to make sure that we still get the same end result as if we'd executed those transactions serially. Just to point out, no transaction is executed more than 2 times, and this rescheduling is quite cheap because data is generally in cache upon re-execution. So this is an important point to make. In this situation where we had to re-execute transaction number 3, we're going to have to step through the same bytecode as before. But when we run into the inputs that we need to load, like the sload opcodes, that data is almost always in cache now because it was previously used the first time that we execute it. And so this re-execution is typically very cheap. And lastly, this is just a simple algorithm. There's no access lists involved. So there's no pre-specification of dependencies for transactions. All of the dependencies are just handled under the hood on the fly. All right, so that was a simple explanation of this simple, intuitive, powerful algorithm, which we call optimistic parallel execution. The last concept I want to mention very, very briefly is the notion of MonadDB. And I'll give a very quick description of it to try to give you a better sense of why this is needed. So at the end of the day, efficient parallel execution ultimately depends on efficient state access. The biggest bottleneck for execution is not the CPU time. It's not the process of having the CPU add two numbers together or do division or things like that, or do jumps. All of that logic is actually very, very simple in most smart contracts. Rather, the most expensive part of execution is always reading from disk and writing back to disk. It's accessing the state. And so the cool thing about optimistic parallel execution is it means that many reads and writes are being surfaced in parallel. So we're basically initiating a whole bunch of reads and writes in parallel. But the bottleneck is still ultimately the disk, because all state lives on disk. And so the whole goal is to get the disk to be much more performant. And in order to do that, we need better software. So just to mention really briefly, modern SSDs are very powerful. They have high bandwidth. However, they have high latency as well. So you can think of an SSD as a bottle with a very wide bottleneck of about 1 million IOPS or IO operations per second. And it's really important to saturate this bandwidth and basically be able to do many lookups in parallel in order to maximize the capabilities of this wonderful hardware. Last thing to know, Ethereum data lives in the Merkle-Patricia tree, and existing clients like Geth or Reth or others store that Merkle-Patricia tree in a database like LevelDB or PebbleDB. And these databases under the hood actually use another tree structure. And so this is very suboptimal, because now you have one data structure that's being embedded inside of another one. So navigating to any leaf in the Merkle-Patricia tree is going to require lookup into another tree for each of those nodes that are being visited. And so this effectively means that there's a huge amount of back and forth with the disk just to do one lookup. That's a lot of sequential lookups. So it means that the SSD's IO capability is not going to be saturated. So MonadDB is just a custom database that stores the Merkle-Patricia tree natively on disk. It uses full async IO support, and it has a lot of other optimizations like bypassing the file system. And the result is that with this new piece of this new database, which is built completely from scratch, we now have parallel access, which ultimately massively accelerates parallel execution itself. So I will wrap up right here in the interest of time, but thank you guys so much for listening to my overview. Just really briefly, if you have questions, feel free to reach out to me on Twitter. My handle is KeoniHD. Thank you so much for listening.
Keone, thank you so much for that amazing overview. And I think you did a really actually amazing job in visualizing how that swim lane execution works. And this is actually super cool. So I'm glad that you're able to make this work. And thank you for taking the time and doing this in a whole different part of the world. So appreciate this.
Awesome. Yeah, thank you for having me.
All right. With this, we are ready for our next talk. And for this next piece, I want to bring on Uma to talk about ZKVMs and how you can roll up everything with SP1. So without further ado, let's welcome Uma. Hi.
Hello. Thanks for having me, Karthik. Yeah, my talk today is about how every rollup will become a ZK rollup and how SP1 or ZKVM can help with that. I'm Uma. I'm the co-founder of Succinct. So first, I think it's important to kind of talk about why ZK rollups are important. So today in the Ethereum ecosystem, there's a lot of discussion about how in this rollup-centric roadmap, the variety of rollups presents problems for users. So in particular, with the optimistic rollup architecture, you have to wait 7 days to withdraw funds from your rollup. And so ZK helps solve that by having faster finality for rollups. Another problem with the rollup-centric architecture as it is today is that interoperability between rollups is pretty difficult. So if I have funds on one rollup, it's hard to bridge them to another rollup if I want to use an application on another rollup. And so with ZK, now you can have proofs for every rollup, and then each rollup can verify proofs of each other. And now you can have seamless interoperability and unified liquidity across the rollup ecosystem. And overall, I think ZK is basically the only way that a lot of these problems for the Ethereum rollup-centric roadmap will actually get solved. And in the end, we'll have a lot better UX if every rollup is a ZK rollup. Now, intuitively, I think this makes sense if we zoom out a bit, because decentralization fundamentally imposes a high overhead because it requires redundant computation. Ethereum is the world computer, but there's many people re-executing the same transactions on the world computer, which is why it's slow and expensive. And inherently, ZK fixes this. So it should be no surprise that ZK rollups are the way we're going to scale Ethereum. So today, ZK rollups do exist because I think a lot of people acknowledge that it is the end game. And what is the current state of that? So first to talk about, what does a ZK rollup require? What it requires is actually pretty simple. It requires a zero knowledge proof of your rollup state transition function, which basically takes in an old state root plus a bunch of transactions and then gets a new state root. And that proof is verified on chain. And today, a lot of teams have put in a lot of work to make ZK rollups, including ZK Sync, Scroll, Polygon. And you can see some code that actually implements this zero knowledge proof of the rollup state transition function. And it's a bit small, but in general, it looks very complicated. It requires handwritten assembly, custom circuits, and overall a bunch of cryptography expertise. So that kind of leads me to the problems with the ZK rollups of today, which is that the first biggest problem is that they require these large specialized teams with ZK expertise to create them and maintain them. Because all the ZK rollups of today are customized, basically those teams write a specialized circuit to make the rollup state transition function. It's very hard to maintain and upgrade. So for example, every 6 months, Ethereum gets a new upgrade, people add more functionality, they change the EVM a little bit. Then you have to go back to your custom circuit and modify it and update it. Another problem with this approach is that there's a really large surface area for security vulnerabilities because you have often code bases that are hundreds of thousands of lines of code. And then finally, another problem is that often these rollups are not fully EVM compatible. So there's this kind of classification of type 1, type 2, type 3, type 4. And most of the ZK rollups today are type 2 or type 4. And there is one type 1 ZK rollup today made by the Polygon team, but it's not yet in production. So overall, the landscape of ZK rollups is that people acknowledge it's very promising, but the way they're built today with the customized approaches is problematic. So the main focus of my talk is about how SP1 plus the open source Rust ecosystem can help solve this problem. So what is SP1? SP1 is a ZK VM that we're building at Succinct that's really fast, and it enables any developer to create real-world zero-knowledge proof applications by simply writing Rust. So how does this work? Basically, if you're a developer, you just write a program in normal Rust code. Then it gets compiled to RISC-V bytecode. So that's RISC-V is a reduced instruction set. That's what the RISC part stands for. And it just has a bunch of opcodes that are simple that your program gets compiled to. And then in SP1, we prove your RISC-V bytecode, which is also called an ELF, and generate a proof of it. And what the proof does is it shows that given a particular program, or rather given a commitment to a program, the program hash. If you run it with asserted input bytes, then it results in certain output bytes. So that's your zero knowledge proof. And once you have SP1, what's really magical is that you can write a zero knowledge proof of a rollup state transition function just using normal Rust code and then running it in SP1. So let's kind of look at the before and after difference of, the pre-SP1 paradigm of doing ZK rollups and then with SP1, how things change. So before SP1, as I was mentioning, the existing ZK rollups of today, required a lot of expertise to write your state transition function as a zero knowledge proof. With SP1, it's as simple as just, writing a normal Rust program. Before, it was really hard to customize and maintain and upgrade your zero knowledge proof of your rollup state transition function because it was such a customized, specialized circuit. Now it's really easy. You can just update the Rust libraries. I like to joke it's easy as cargo update ref. Finally, a lot of the concerns around the security surface area are also reduced because instead of having a custom 100,000 line code base of, a lot of ZK circuit stuff, you just have an existing code base that is often already audited. For example, ref got an audit recently. And then we can take ref and run it in SP1, and then the audit and security surface of ref, which is being used in production by many different people, compounds to running ref inside SP1. Finally, you get type 1 EVM compatibility for free because, ref is obviously type 1 compatible. It literally is a Ethereum node implementation. And then finally, with SP1, one of its major breakthroughs is that doing all of this is actually not that expensive. The proof generation costs are actually pretty cheap, and I'll get into some concrete numbers later. Okay, so I've kind of, at this point, pitched the dream of, just take ref, run it in SP1, you're going to get a ZK rollup, and it's going to be simple and easy. So now let's actually walk through the steps. Okay, so if you want to generate a proof of executing an Ethereum block within SP1 using ref, there's a few steps to actually writing this program. So the first step is that you have to actually given a block, you have to actually execute it. And you have to fetch a bunch of Merkle proofs and all the storage accesses and all the accounts that you're touching during the execution of the block. And the way we do this is we have a database that is connected to an RPC, and we simulate the execution of the block with the RPC. And every time we touch an account or touch storage, we use the RPC to fetch those values and the corresponding Merkle proofs. And this happens in a host program that's basically simulating the execution before we actually generate the zero knowledge proof. Then afterwards, after we execute the host program, our next step is to actually construct a client input with all of that data. So the SP1 program, we also call that a client program. That's the actual program that's getting run inside SP1 that we generate a zero knowledge proof of. Obviously, within that program, we don't have access to an RPC or a file system or anything like that because it's running in this embedded environment inside SP1. And so we have to pass in all the data that we might need to do block execution. So what do? From all the data we fetched in step 1, we construct an input to our client program that takes in the current block, the previous block against which we're going to Merkle prove all of the state that we touch. We put in all the storage proofs, and then we put in some extraneous try nodes that we might need, and we construct this client input. Finally, we actually execute the client program. So this is the actual SP1 program that's executing an Ethereum block. We read in the input, we deserialize it, then we actually execute the block, we compute the block hash, and then we commit the new block hash after execution. And then we actually generate the proof in SP1 using this program. There were some pretty interesting challenges we ran into when actually trying to do this. It sounds simple enough, but in reality, there was a few hurdles that we had to solve along the way. So one of the first challenges was ref, which is the Rust Ethereum client implementation, didn't actually compile in SP1 when we started this project. The reason for this is within SP1, as I mentioned, you don't have a file system, you can't make network calls. So if you use certain crates, they won't compile with an SP1 for good reason. And we get to collaborate with the Reth team to basically get rid of those crates, or feature flag them or gate them inside the certain Reth crates that we wanted to use. Another challenge we ran into was that state root computation in the EVM is always very difficult. The Merkle-Patricia trie and RLP are not friendly data structures or algorithms, and usually the state root is computed from a disk-based database. In our case, it's a fully in-memory database, and so we collaborated with the Reth team to compute the state root in an efficient way. And then finally, the Ethereum Merkle-Patricia trie, which is the data structure they use to actually store all of the storage, has a lot of edge cases. And there were certain debug endpoints that we had to use to get all of the relevant data. In the end, we came up with a repo that's around 1,000 lines of code total that just imports Reth, does all the stuff I described in the previous slides, and gives us Ethereum block execution within SP1, which is pretty awesome. So it's like you get a ZK EVM and 1,000 lines of code. And now for everyone's favorite part, kind of what are the proving costs? What are the proving time associated with all these things? So I took a range of random blocks. You can see they're sequential, so it's not really cherry picked. And this table shows the results of actually running SP1 Ref and generating a proof, and shows the cost, the proving cost per transaction. So, if we dive into this table a little bit, you can see for each block, we have the gas used in that block. Normally, the Ethereum gas target is 15 million gas. So you can see a lot of these blocks are a little under that. Some of them are over. And the column that has the number of cycles is the number of RISC-V cycles. So the number of RISC-V instructions we use to execute the program. You can see for the bigger block, the 25 million gas block, we use a lot more cycles than for a smaller block, for example, like the 12 million gas block. And in the end, how we basically compute the proving cost per transaction is we generate a proof for the block on a GPU. In this case, we're using a Lambda Labs A6000, which is a cloud provider similar to AWS, specialized for GPUs. So we run it on this particular GPU in the cloud. We take the end-to-end time it took to generate a proof. We multiply it by the on-demand cost of renting that GPU in the cloud. And then we divide by the number of transactions in that block. And in the end, we end up with a proving cost per transaction. And you can see for these blocks, it's 0.2 to 0.3 cents, which is pretty awesome. So the main takeaway from this slide is that actually with executing Ethereum, generating proofs of execution of Ethereum blocks using SP1 plus Reth is actually super cheap. It's 0.2 or 0.3 cents per transaction, which is really awesome. And the question people often ask is, wow, that sounds really cheap. How is that possible? And that's in part and significantly due to SP1's, novel ZK innovations and a lot of performance engineering. So now I'm going to kind of walk through how SP1 is, so cost effective and fast at, actually generating proofs of Ethereum blocks. So one of SP1's novel innovations was this notion of a precompile centric architecture. To talk about what a precompile is, in SP1, as I mentioned, it's a RISC-V ZKVM. So most of SP1 is just proving that we execute the RISC-V instruction set correctly. But for very cryptographically heavy operations like hash functions like catch-ACK or SHA, or elliptic curve arithmetic, which is used for signature verification, like ECDSA signature verification with the SEC-P256K1 curve, or BN254 or BLS 12381 arithmetic, we have these specialized ZK circuits in SP1 called precompiles that connect to our main RISC-V CPU. And basically, for those operations, we dispatch to our specialized circuits and we generate proofs of those specific operations in those circuits and connect them back to our main CPU. And what this enables is that instead of spending, hundreds of thousands or sometimes millions of RISC-V cycles, we are able to reduce the cycle count by between 6 to 10x. And we'll use our specialized circuit, which is a lot more efficient, to generate proofs of these cryptographic operations. It's kind of similar for those of you who are familiar with writing really specialized assembly. In a normal CPU or programming context where for code that needs to be really, really optimized, that's run many times, you write assembly and it's very, very performant and fast. And then for other parts of your program, you just write, normal code in a higher level language. And so our precompile centric architecture in the end helps reduce cycle count by, sometimes up to 10x. And that reduction in RISC-V cycle count directly translates into a 10x reduction in proving time. And so that's why SP1 is an order of magnitude faster than other ZK VMs. Other performance engineering optimizations we did include writing a full GPU prover for SP1. So GPUs are these machines that are really, really good at executing parallel computation. And ZK proving is a very parallelizable computation. And so when we wrote an SP1 GPU prover, it improved the cost and latency of SP1 proving by over 5x over our CPU prover. And intuitively, the reason for that is if you use $1 worth of compute on a GPU, that gets you just a lot more flops or operations than doing $1 worth of compute on a CPU. Finally, there's a bunch of other cryptographic algorithmic optimizations we did for SP1. So we have like a pretty novel memory argument that doesn't pay for Merkleized memory, which is the traditional way of doing memory in a ZK VM context. And then we have this multi-table batch fry scheme that lets us only pay for the opcodes that we use instead of having to pay for everything at once. And yeah, there's a bunch of other cryptography optimizations that I could spend a very long time talking about that make SP1 really fast and awesome. So yeah, the main takeaways from kind of this section are that the costs are really cheap. And, the estimates I gave in this talk are really pessimistic. We've been working on a bunch of performance improvements. And you can also, instead of renting a GPU on demand in the cloud, you can basically reserve a GPU instance for a year, which is a lot more cost efficient. And in all, we think these costs can go down by another 5 to 10x. But really the magical part is that this is super minimal lines of code. It's really easily customizable and upgradable, and the surface area is really small. We were able to generate proofs of Ethereum blocks with 1,000 lines of code by just running it in SP1 and importing ref. You can add new precompiles when you want, using, ref makes that very easy. When Ethereum upgrades, you just update to the latest version of ref. And overall, in the end, this is just the best way to make a ZK VM because it's such a minimal surface area. It's so easy. It's so customizable. The security compounds. And that is a very, very powerful developer experience. So that is like the truly magical part about SP1 ref. So I've talked about now at this point how to generate proofs of Ethereum blocks by taking ref, running in SP1. But now there's actually a lot more to be done to build a full ZK rollup. And this is a really good kind of meme to illustrate the point. We're on step 1 of making a ZK rollup, which is we proved the execution of Ethereum blocks. But now there's so much else to do, including sequencing, batching, like having your whole protocol, having your smart contracts on chain, etc. So that brings me to the next part of this talk. So the OP stack is familiar with, or is probably something you guys are all familiar with. It's a modular open source toolkit for building rollups made by the Optimism team. And this is a concept that was made popular by the Optimism team a few years ago. And they, in their blog post they published about it, they said not just rollup, not just optimistic, which means they kind of designed it from day one to be really modular and upgradable and one day have ZK proofs. And that's exactly what we did. So this diagram here kind of shows the OP stack's design and architecture. And it contains a lot of the other parts of the rollup that go beyond just, generating proofs of Ethereum blocks. So they have this OP Badger component, that's the sequencer that takes in user transactions and posts them to the DA layer. They have an optimism portal that basically that users interact with to deposit money into the rollup and withdraw money. They have an OP node and OP get that's actually responsible for maintaining the rollup state. And then they have OP proposer, which basically queries to an RPC and then actually proposes the state routes to this L2 output Oracle contract that has the state of the world against which users can withdraw funds. Now today, all the stuff in the red involving OP Challenger, OP Program, Canon, etc., is the optimistic fault-proof challenge system that the OP stack uses to adjudicate the outcomes of the OP proposer. So in particular, the way their system works is that the OP proposer proposes a state route, and then there's a fault-proof game adjudicating whether that state route is actually correct or not. And this is the interactive bisection stuff that's going on. So what we did to turn OP stack into a ZK rollup was actually really simple. We replaced all the stuff in red related to the fault-proof game that we no longer need with a ZK proof. And we changed the L2 output Oracle to now, instead of just taking in the new state route from the OP proposer, it also takes in a proof that verifies that there's a valid state transition function from the old state route to the new state route. And the ZK OP proposer is a new version of the OP proposer that is responsible for querying to get proofs from our async prover service, and then actually proposing those state routes plus a proof to the new smart contract on chain. So to actually dive into these components and go into more about how we built this stuff, one of the biggest things we had to do was actually implement a ZK proof of the OP stack state transition function. So in our case, the OP stack state transition function isn't just executing Ethereum blocks. It also includes a bunch of other logic, like taking the data that's posted to L1 and deriving what the L2 transactions are, and then having some other extra logic around deposits and withdrawals and things like that. They call this the derivation pipeline. Now, thankfully, the OP team made this library called Kona, which is written in Rust, to actually implement the OP stack's state transition function in Rust code. So what we were able to do was just take Kona and write a very short, 500 line of code program and run it with an SP1 to get a zero knowledge proof of the OP stack state transition function. And then with that program, we were able to verify proofs of that in our ZK-L2 output Oracle. And then once we had that program, we used SP1 to generate proofs of it. And our ZK OP proposer is this actor that basically runs in a loop. It pulls the tip of the chain. It uses the succinct prover network to generate a proof with one API call, and then it proposes the new state route with the proof to the ZK-L2 output Oracle contract. To dive a little bit into how this actually works, basically the ZK OP proposer follows the tip of the chain, as I mentioned. It takes in ranges of blocks and it generates a proof for that range. Now, ranges of blocks have their proofs generated in parallel because, for example, a range of blocks across 1 minute, the proof might take 10 minutes to generate, but that's no problem. We just run those proofs in parallel. And then when we have all those proofs, we finally aggregate all of them together across a range of blocks for 1 hour and then post that on chain. And so when we combine these pieces together, we made this repo OP succinct that lets you take any OP stack chain and turn it into a full ZK proven chain in 2 really simple steps. So you can take any OP stack chain that's deployed with RAS or your favorite RAS provider or even an existing one. And all you have to do is you have to deploy one L2 output Oracle smart contract. And then you have to run this ZK OP proposer that's basically generating these proofs. And then you update them. You update the smart contract with these proofs. And so those 2 components of your system are running as I had previously described. But it's super simple. It's 2 easy steps. It takes 1 hour to do this transformation. And then in the end, your time to finality goes from, the 7 days of a normal OP stack rollup, which is needed for the optimistic fault proof window, down to 1 hour, which is super awesome. And you can check out this repo here. It's at succinct.lab/op-succinct. And in the end, we ended up with around 2,000 lines of code to do all this stuff, thanks to the great work of the OP team and their modular design and architecture that made it super easy to just slap these components right in. And the great work they've done on Kona, which is their Rust implementation of the state transition function, and SP1, which makes it really easy to generate ZK proofs of Rust code. So when you combine all those pieces together, you're gonna get a full ZK rollup in less than 2,000 lines of code, and 2 easy steps, and that is super magical. So as I mentioned, yeah, we actually ran this. We made this repo. We actually tested this for OP Sepolia, and we were able to actually keep up with the tip of the chain with 1-hour finality using our ZKOP proposer, which is pretty awesome to see. Now, to quickly cover the costs and the latency, in any ZK system, there's kind of 2 costs. One of the costs is the on-chain costs of posting a ZK proof to Ethereum and then actually verifying that proof. Generally, verifying a ZK proof on Ethereum takes like 280K gas. And in our case, when we change the ZK contract, the L2 output Oracle contract to accept and verify ZK proof, it ends up taking around 420K gas total to propose the new root and verify the proof and do some extra logic around storing this information. This is actually the same amount of cost as the normal fault-proof dispute game that OP uses, which has some overhead from they have to create a new contract and do a bunch of stuff for their normal fault-proof dispute game. And so in the end, when you use an OP succinct rollup with ZK proofs versus a traditional OP rollup, you actually use the same amount of gas on chain. So you're not paying Ethereum any more gas, any extra gas, which is pretty awesome. So the on-chain costs stay the same. The main extra cost comes from off-chain proving costs, which is the actual cost of generating these ZK proofs. And we benchmarked and found that roughly the proving costs are between 0.5 to 1 cent per transaction in an average case. And this is super rough. It really depends on your workload. It really depends on your rollup. Actually, for rollups that have much higher TPS like Base, the costs per transaction go down because there's a fixed cost to proving blocks and reading data from L1 that can get amortized across more transactions. But already 0.5 cent to 1 cent proving cost per transaction is really cheap, and we think this can go down a lot, which I'm going to cover in my next slide. And then finally, the interesting piece is latency. So typically, we're generating proofs for every range, and then we aggregate them together every hour and post it to Ethereum. A lot of people like to ask, can this be faster? Can I have finality that's every minute or 10 minutes or something like that? Because it costs 417K gas to actually verify these proofs and post a new root. If you were to do that every minute on Ethereum, that'd be a very good way to quickly lose a lot of money. And so really one of our biggest bottlenecks to finality is actually the Ethereum costs of posting proofs. And so today we generally post proofs every hour. And so our current latency when we did it for OP Sepolia was that we had a 1-hour latency behind the tip of the chain, which again is pretty awesome because you go from 7 days to 1 hour. If we wanted to do it faster, the rollup operator could configure it to go faster. The proving costs end up being the same, but you're just paying Ethereum more for faster settlement. Another thing to note here is that latency is not the same thing as throughput. So by scaling the number of machines that we do proving on, we're able to keep up with really any chain that we want. And the latency stays the same no matter what. Another interesting point to mention is that people are always wondering about the security of these systems. And one nice thing about this approach is you can actually layer multiple methods of security in addition to ZK to get really, really secure rollups. So you can have a whitelisted set of proposers who can post proofs. You can even add a small challenge period after a root is proposed and a proof is verified for a permissioned actor to step in and delete roots in the case of bugs. And conveniently, the OP-Stack repo already provides this kind of functionality. So in the end, you can end up with a system that's really secure that combines ZK plus a bunch of other safeguards to make sure that even if your ZK proof fails, if there's bugs in the system or bugs in your program, you're still safe. And I want to finally cover the kind of 10x cost reduction that I talked about previously. So even today, we're at basically between half a cent to 1 cent of proving cost per transaction for an OP stack rollup, which is already, pretty awesome. I think the average cost per transaction on base and OP across the past 30 days were between 1 cent to maybe around like 5 cents in the case of OP. Last I looked at a Dune dashboard. So already, 1 cent or half a cent's no big deal, but we're always working on getting this better and reducing the cost even more. And so I want to talk about some of the ways we think SP1 can really decrease its costs in the next year. So one of the main methods is that right now, a lot of our costs are benchmarked on on-demand GPU instances in the cloud. But if we're able to take GPU instances and buy them and reserve capacity for a year, or even do on-prem GPU deployments, that's a lot more cost efficient than having to pay AWS a really big margin. We also are releasing a new system soon that has a lot more algorithmic improvements to arithmetization, a better memory argument, a better recursion argument that should hopefully compound and stack to a 3x or maybe even higher improvement on just SP1's algorithmic efficiency. And we're always working on novel algorithmic optimizations and new techniques in ZK to make SP1 better. Another interesting source of improvement is actually at the OP stack protocol level and the Kona level. So when the OP team was building the OP stack and their protocol, they weren't really thinking about the cost of ZK proving it. And so currently their protocol requires iterating through all the L1 blocks. And that's something that we bear the cost of in our ZK program. But this is super easily fixable with the nonce. And there's other things they can do, like, for example, adding a incremental Merkle tree on chain when posting new batches to make the ZK overhead go down significantly just from their protocol. And these are really small things that could be done to improve the cost efficiency, maybe by like 2 to 3x just from the protocol. And another thing that we want to do is actually profile our SP1 program that uses Kona to make it really efficient for RISC-V. So right now there's a lot of stuff that when you do on a CPU, it's not that intensive, like iterating through things twice. But in a ZK context, a lot of that stuff can add up. And, the 50% here or there really matters. And we think there's a lot of, room to squeeze out performance just from simple profiling and benchmarking of Rust code, which is also pretty awesome. Okay, so yeah, if people are interested in learning more, you can reach out to me. You can check out these repos. The first RSP repo is about taking ref and running an SP1. The OP Sysync repo is about, converting your OP stack rollups into ZK rollups. And yeah, I hope that SP1 rollups will be the future of how Ethereum scales. Thank you.
Amazing. Uma, thank you so much for going so in depth on how everything works and all the performance improvements you can expect in the future. So this was really awesome. Unfortunately, we don't have enough time for questions, but if we have any questions from the chat, I'll just relay them to you directly. But I really appreciate you taking the time to do this amazing talk.
Thanks for having me.
Amazing. All right, next up is our last panel for the summit. And for this, we're going to talk about multiple current proposers. And for this amazing panel, I'm going to bring on Mark from OP, Max from Special Mechanisms Groups, and Justin Drake from Ethereum Foundation. And moderating this discussion will be Liam from ETH Global. So without further ado, let's welcome all of them on stage.
Okay, thanks, Kartik. Awesome. Okay, so we are going to talk about multiple concurrent proposers. This is a very hot topic in Ethereum these days, and we have, I think, like the best possible people at the table to talk about it. I think this is also somewhat of a dense topic. It relates to base sequencing, it relates to pre-confirmations, superchain, interop, MEV. I think if we can do a great thing here of teasing it out and helping people understand all the components, that will be like a great value add to the community. So let's give it our best shot. But I'll introduce kind of the panelists. So Mark Timeway is co-founder and one of the kind of tech leads building out Optimism and the OP stack, superchain, interop vision, and everything. Max is at Special Match, and he recently kind of put together the proposal for Braid and multiple concurrent proposers. So we're going to get kind of a deep dive into that from him. And Justin Drake obviously is one of the core researchers at the Ethereum Foundation. So to kick us off, I wanted to kind of just go to each of you guys and kind of just have you introduce kind kind of where you're at on this topic, what you've been working on related to it, and then Max specifically, I'd love if you could kind of describe multiple concurrent proposals and what is that exactly? What does that mean in the context of kind of Ethereum's future? So maybe let's start with Max and then go from there.
Yeah, thanks for having me. I guess I'll start with where we started on multi-proposer. We being myself, Elijah Fox, and Malesh Pai. Malesh Pai is a professor at Rice who also works with us at SMG. And basically, we started with this question of how to solve LVR. For those of you not familiar, that's loss first rebalancing, which is this problem where the DEX prices on chain are not correctly set to the Binance prices because the Binance prices move, and then there's some risk-free arbitrage available, and that value from the arbitrage generally doesn't go to the LPs who are getting picked off. It generally goes to the proposer on Ethereum L1 or the sequencer on an L2, whoever controls the ordering, and we kind of said, why don't you just hold an auction for the right to do that? And then we, having that idea, said, is it possible to hold an auction on Ethereum L1 for an LVR recapture auction? And the answer, it turned out, was actually no. And the reason it was no is because it's possible to censor transactions. The builder or the proposer can censor whichever transactions they want. They build a block that has transactions they want. If they don't want certain transactions, they can leave them out. And why is that important? Because if you want to hold an auction, you need to make sure that all the bids get in. If there's one party who can censor the bids, then they can censor all the bids, submit their own stink bid of like 1 cent, and win the item for free. And this is basically what's happening on Ethereum L1 is we do have an auction for the right to capture LVR. It just happens to be that the auction is run by the proposer and all of the proceeds go to the proposer. That auction is called the MEV Boost auction. So we kind of set out on this problem of how do we increase the censorship resistance? And the first thing we did is we looked at the related literature and we found a blog post from Vitalik in 2016 that basically made a very similar point, which was that censorship resistance, which we often think about as kind of this long-term censorship resistance designed to help, the North Koreans or whatever get on chain. At the time when Vitalik wrote this post in 2016, the Silk Road was what he talked about. He said, censorship resistance isn't just important for Silk Road to be able to operate on chain. It's actually important for the fundamental integrity of financial applications on chain. And just to close it off, basically, the solution we came up with for how to increase censorship resistance was to eliminate the proposer monopoly. Eliminate the fact that there's only one proposer who gets to put transactions on chain, and that's how we got to this idea for multi-proposer, and Braid is a specific concrete proposal for how to do that.
That makes a lot of sense. I think we're going to talk a lot about Braid from there. Justin, do you want to introduce yourself and comment on your take?
Sure, I am Justin Drake, a Ethereum Foundation researcher. I guess in my mind, there's two forms of multi-proposing. There's this idea of multi-including, where the multiple proposers include transactions on chain. And then there's kind of this other flavor, which is multi-sequencing, which is what Max, I think, is trying to advocate for, which is that in addition to including transactions on chain, there is some sort of ordering rule that is applied. And one of the directions that we've gone down at the Ethereum Foundation is towards the multi-including side of things. So we have this notion of inclusion lists where even if there's, one evil builder who's building 100% of the blocks, we still want transactions to go on chain. And the simplest version of inclusion lists is that at every slot, you just have the one proposer that proposes an inclusion list. But recently, there was a proposal called Fossil that basically suggests having many proposers or multi-proposers doing the inclusion of transactions for censorship resistance. And I think there's some common intersection with what has been researched with Ethereum Foundation researchers and Max, which is specifically this idea of having multiple proposers put transactions on chain. I think kind of the new design space that Max is opening up is this idea of putting an ordering rule in addition to just having multiple includers, and it's very, very interesting in potentially solving the MEV problem, not just in terms of distributing it equally or segregating it from the proposers, but actually like at the root, making sure that it's kind of unextractable in some sense. So it's a very extreme proposal, which is great because we want to try and analyze the design space. Having said that, my personal position as of today, and I'm open to change that position, is that there are like fundamental complications that come with this multi-sequencing, this where you have this ordering rule, and basically part of it comes from the fact that you have a generalization of multi-slot games. So one of the things we're worried about is what if a single operator controls multiple slots in a row, they can start playing games. But now there's another question which we need to ask ourselves is what if there are multiple proposers that are controlled by a single operator within one slot in the space dimension, so multiple blocks in braid within the same slot. And I think I've identified like a few attack vectors that I think need to be addressed. Otherwise, it's possible that that multi-sequencing with the ordering rule will introduce centralization vectors due to the fact that it unfairly gives an advantage to large operators that control many validators.
Can I just respond to a few points? So first of all, I would say I don't agree with this dichotomization of multi-sequencing, multi-including. I think we should just throw that out because it's actually just confusing for people. Braid and Fossil are both censorship resistance technologies. There are separate ordering rules. There's a proposed ordering rule, which actually I would say has not been sufficiently fleshed out in the Fossil, which is basically how to merge all the transactions that you get together. And I think it's actually very unclear what the Fossil proposal wants to do for that. I'm not even sure the people who came up with it know what the ordering merge rule that they want to do is. But you can do that same merge rule with Braid. Just designate one of the proposers in Braid to fill the role of the execution proposer in Fossil, and you can do exactly the same ordering rule. And so I think this thing that you've been pushing, Justin, of the multi-including, multi-sequencing, trying to paint Braid as a bigger change than it has to be. It's really just an alternative to Fossil on the inclusion dimension. And so I don't think it's fair to lump a thing that is inherently ordering rule agnostic and could include the vaguely specified ordering rule that has been suggested for Fossil on top of it as well, is to paint that as being somehow related to priority ordering is I think like a false thing to do because it's actually not that.
So right, I agree that like you can take Braid, you take in Fossil, and you can either not have or have the ordering rule. I guess like just you as a person, I think are a proponent of having this ordering rule, and I'm a proponent of not having it. And by having an ordering rule, I basically mean that the ordering is determined by these k proposers that are participating in one slot. Like the alternative vision is that the k proposers are only including transactions on chain, and then there's a separate entity, like a separate proposer, if you will, in the slot after that, who can decide on the ordering with the constraint that they must include the transactions in the inclusion list.
Well, I think, I would say I am a proponent of that, but I think it is disingenuous to say I have issues with priority ordering, for example. Therefore, Braid is invalid, when I would just say if you just line up Braid and Fossil together and you just look at the technical merits, one of them creates a large last look, requires additional rounds of communication for the percolation of the inclusion list, and one of them doesn't. And so even if you're a proponent of having a kind of somebody fill the role of the execution proposer, build a block through some MevBoost type of thing, and then just have inclusion happen on the other threads there. It's still worth considering whether Braid or Fossil is better to serve as the inclusion gadget there. Does that make sense, what I'm saying?
Yeah, it makes sense. I think we're like arguing on definitions. I'm not trying to bucket Fossil or Braid into one specific category. I'm just talking about design philosophies, about either having this ordering rule or not having it. And I think just generally as a researcher, like your stance is that you want this ordering rule, and my stance is that I would be cautious about having this ordering rule.
Yeah, but just to reemphasize, I think like we can talk about the ordering rule, but it's a separate question from whether Braid is better than Fossil. So, like, if you say I think that the ordering rule that is proposed by Fossil is better, okay, that's fine. But then we should also have a separate orthogonal argument about whether Braid or Fossil is better for the censorship resistance part of it, because that's the whole point of my argument. Is basically execution and consensus should be separated. Consensus should provide censorship resistance in the short term, which it's not providing today. And the ordering rule is something that should happen at the execution layer, and we can argue about what the best thing to do there is. And if you think we should give all the ordering power to one person, which I think is clearly wrong, but we can argue about that point. But it's a separate point from whether Braid or Fossil is better.
Agreed.
Nice. Okay, so we dove very deep, very fast into Braid and Fossil. I think that's great, but I think I want to zoom out a little bit and get a sense of why are we even kind of in this debate in the first place, and practically what are we going to have to actually do? Because one key part of kind of Max's argument before is that we're kind of seeing a world right now where L2 networks like Optimism with OP mainnet, with Base, are kind of beginning to take this huge amount of kind of the DeFi universe, and liquidity starting to moving into them, users starting to use them more, and we just are entering into a world where Ethereum kind of needs to figure out how does it evolve, and then networks like Optimism have a pretty important role to play in either adopting into Ethereum's roadmap or being a counterbalance against it or whatever. And so I think we need to get into the question of like, how is that going to play out? So maybe Mark, do you want to kind of just paint a picture of like, where do you see Optimism fitting into all of this, and how do these different schemes, Braid, Fossil, or more generally multiple concurrent proposals, how does that relate to the roadmap of Optimism?
Yeah, totally. So right now is the time to scale. Like, I think that we have everything in place to build applications that people actually want to use. And we just need some like visionary product people to go to market and actually like build the apps. So through all of this, it is time to scale. So we need to figure out, where the roadmap of the OP stack should go. Like, what does it mean to really scale? And I think this is like one thing a lot of people always complain about is they're looking for a decentralized sequencer. What does a decentralized sequencer actually mean? And I think everyone kind of has their own value judgment on what decentralization of an L2 actually means. And to me, when I think about decentralization of an L2, I think about leader election. And I also think about some ability to join the set of leaders. And really, one possible end game is, you literally have data centers of sequencers, and they're able to process transactions really, really quickly and super high throughput, and they can serve the entire world, while at the same time still maintaining the nice properties, like the security properties of L1 Ethereum. So how do we get there, right? And I'm here to learn, basically. I have no idea which, route is the best route. So hearing all these debates, it's super helpful. One thing that I would like to raise is that, we've been thinking a lot about ordering rules. We do kind of think the priority fee ordering rule is really nice. A lot of chain operators that are running sequencers, they like this idea of this priority fee ordering. The chains right now are earning a lot of money, and then as applications, because if you look at the revenue differences between an L2 that runs priority fee ordering versus first come, first serve. The chains that run the priority ordering, they earn a lot more. And this could actually just be due to wallets. Some wallets submit priority fees that are too high. So those sorts of bugs. It could just be wallets that are like paying too high priority fees. That could be the case. I have no idea. But we need to scale. And basically what I'm saying is I'm here to learn from you two on what we should be thinking about and be taking seriously as we scale our L2 sequencers.
Yeah,
that makes a lot of sense. And I think it's I'll just kind of see that. I think it's a fantastic prompt, maybe for both Max and Justin. Like, what's the pitch?
Well, yeah, let me follow up on the bull case for priority ordering. First, I'll say on the wallet side, I checked. We had a discussion after yesterday's Twitter drama about the priority ordering. I checked. I think the thing that we noticed on MetaMask wallets submitting type 0 transactions was actually a bug on the block explorer. So I checked on our end, and it's actually not happening. So we do submit type 2 transactions with low priority fees on MetaMask side, at least. I don't know about other wallets. And this was on Base because we noticed that Base revenue was very high priority fees. So what was that about? Well, actually 8% of that was from a single arbitrage bot. So 8% of all of the priority fees on all of the network, which is like 6% of the total revenue that Coinbase is getting from Base, is from a single arbitrage bot. So this is like good in that Base is making money, but it's bad in that the arbitrage is coming out of somebody else's pocket. And it's not as simple as that. It's not just a transfer from the LPs to, Coinbase's wallet. It's actually more sinister than that because it causes all sorts of downstream effects. It increases the spread, which makes traders get less when they put money in, they get less out because the spread is wider. And this is like undesirable. My goal in making a blockchain is basically make it credibly neutral, lower frictions as much as possible, which means have spreads as tight as possible. And that's one thing that the priority ordering can give you, which currently is not necessarily enabled. But there's this thing that Dan Robinson proposed, which is called MEV taxes. What it does, it allows the smart contract to read the priority fee and charge additional fees on top of that. And this basically, we've figured out, allows the smart contract to operate a very broad class of mechanisms. So it can operate auctions on its own via the priority ordering. So priority ordering isn't just good because it gives revenue to the chain. It's actually good because it gives apps a lot of flexibility to decide their own sequencing and run their own auctions. And again, the reason you want to run your own auction is to distribute the revenue back to the LPs who got picked off. And ultimately that improves the spread, improves the user experience, lowers the friction.
Justin?
So part of the context around the discussion recently is, do the L2s have an incentive to decentralize? And I guess there's like two kind of possible outcomes. One is that they decentralize with a token that they do control. In which case, I don't think that the MEV issue is necessarily that big, and the reason is that if there's a large amount of MEV, then there's a high incentive to be a staker because you will collect that MEV, and that will reflect in the token price. So in some sense, it is captured by the token. But maybe the more interesting question that I'm studying is, does it make sense for an L2 to opt in to a decentralized sequencer that they don't control, which is not using their token? And the reason why they would do so is because they would opt into a shared sequencer, and that would increase their composability. And one of the theses that I have is that by being more composable, by being so-called synchronously composable, you open up the design space. For example, you have shared liquidity, and DEX aggregators like 1inch start working across all the L2s that share share a sequencer, and so you basically have more, congestion fees because there's more transactions, more activity happening on your L2. But the big question to ask is the loss of MEV compensated by the increase of congestion fees? And my personal thesis is that MEV is going to zero. And the benchmark that I have is the L1. If you look at the L1, there's about 800 ETH per day of MEV, and there's about 3,200 ETH per day, on average since EIP 1559 was turned on. And so it's roughly an 80-20 ratio. And I believe that the ratio is going to tend towards 99%, 1%. And the reason is that we're going to have sandwiching be eliminated. We're already actually seeing that. Big wallets like MetaMask are no longer sending their transactions to the public mempool, and so we're not seeing sandwiching there. And then the other big source of MEV is what Max calls LVR, but maybe a more mainstream way of putting it is SexDex arbitrage. And here, as Max mentioned, there's all sorts of new designs by Dan, by Sorella, by all sorts of other teams that don't leak MEV to the sequencer and instead rebate the capture and rebate the MEV to the LPs, and ultimately lowering the spreads and increasing user welfare and liquidity. And so we should expect these kind of next generation DEXs to win out. Now, unfortunately, Sorella is bottlenecked on Uniswap v4. Uniswap v4 is bottlenecked on the next hard fork because and so it's going to take some time before all of this activity, the SexDex arbitrage basically goes down. And if it is indeed correct that we're moving towards a ratio of 99%, 1%, then the question about the way that I phrase it is as an MEV gambit, right? Like by connecting to a decentralized sequencer that you don't control, you lose the 1% of MEV, but you gain more traffic from the additional composability.
So just on these points,
one thought about the decentralized sequencer is this idea of like composability if you kind of opt into a shared sequencer. I think one thing that we're learning a lot right now at Optimism as we're building out this interoperability project is if the assets were not designed to be interoperable, then it's not really easy to interoperate them. And the question that I ask is like, is interop useful if there's nothing actually that can interop? Like, are we just like sharing data, or are we sharing like tokens? And I actually think that we did a lot of product research and we talked to a bunch of different teams, and a lot of teams, they express that they don't care very much about like their tokens being like interoperable between different chains. And we think that really it's mainly Ether is like the one thing that's like really important to make interoperable. It could be the case that in the future, a new wave of tokens that are maybe like L2 native that are designed specifically to be interoperable will exist. So I don't think that interoperating with a shared sequencer is a strong enough incentive to cause an L2 to like give up their sequencing rights until there's actually, tokens, or there's like a reason to actually interoperate more than just like, you can do it, if that makes sense.
No, absolutely. There needs to be some sort of a carrot. And the way that I see it is that if you don't have shared sequencing, you still have interop, but it's asynchronous interop. When you have shared sequencing, you open up the possibility for this more powerful interop, which is synchronous interop. And just empirically speaking, if you look at various blockchain projects, the asynchronous ones tend to not have done so well, with developers and with users, because there's like some DevX pains. If you look at Cosmos or the Internet Computer or Polkadot or Ton, they all embrace this asynchronous, virtual machine and model of execution. And then on the other extreme, you have chains like Solana and Ethereum that have embraced, synchrony and have actually done pretty well. Even Bitcoin is synchronous, even though it doesn't really use its virtual machine much. But I think the interoperability is more than just unifying liquidity. When you have synchrony, you, for example, have access to flash loans, and like basic things that developers take for granted also just work out of the box. So, for example, this idea that what gas price you're paying, right? Because if you have asynchronous interoperability, basically what you're doing is that you're splitting your transaction over multiple blocks. You have sequencer 1 that's kind of starting your action, your user action, and then in some other block, you're completing it with a different sequencer. And you don't know what the gas price will be in the future. You're also introducing reversions. So it's possible that step 1 of your transaction will succeed, but for some reason step 2 doesn't succeed. For example, you buy an NFT on another chain, but someone just swept in and took the NFT before you. Now you need to handle reverts, and things become complicated. If you have a chain of K transactions, it could fail at any of these K positions, and you need to take into account all these different failure modes. And I gave a talk at ETHCC in Brussels specifically on why is synchrony valuable, and I gave something like 15 different reasons. And so there is this long tail, but I think what gives me the most conviction as to why synchrony is indeed valuable is just this empirical observation that only the synchronous virtual machines have been successful so far.
Yeah, I agree. We should scale the L1, right, Justin? Because that
yes,
will be synchronous
absolutely.
natively. Let me just say, I agree with your point on the fact that if you decentralize the sequencer, the token can accrue the revenue, because it's kind of basically just an execution ticket at that point. Like the token becomes partially an execution ticket and gives you the right to propose blocks, and that's where the sequencing revenue is in the right to propose blocks. So I agree on that point. I partially agree on this idea that MEV is going to zero. I would say in the specific example you mentioned of Sorella, they're bottlenecked by two things. One of them is the next hard fork for UniV4, but the other one is that they don't have censorship resistance on chain. And so what is their solution? To build out their own external auction. But why would you do that? Like, why would you have these app developers who want to make next generation DEXs to make this stuff go to zero have to build their own external network and build their own consensus just to have censorship resistance? They should have it in the L1 or on the L2 or wherever they're going. It's clearly product market fit for censorship resistance when an L2 or when a next generation DEX like Sorella is literally going out of their way to build their own whole consensus just to have an auction. We could probably just give it to them and save them a bunch of time and let them focus on gas golfing or whatever else they would use their time on, improving their product, and not have them have to build their own consensus because Ethereum L1 consensus is deficient at providing short-term censorship resistance.
Absolutely, yeah, and I agree with you. Like first, like the innovation should happen at the app layer, just Sorella, they're just tinkering with it. And then once this is a proven, method that, we want to potentially have chains like Optimism have it at L2, and then if that is a successful experiment, then maybe we can consider enshrining it. And I think that's ultimately a very constructive way of going forward.
I guess I'm also curious, Mark, to hear your take on kind of the MEV is going to zero argument, and like how does that play into any thoughts around Optimism and the superchain's philosophy on MEV extraction or not, with regards to how that sequencing ecosystem will work?
Totally, yeah, that's a great question. I definitely generally agree directionally that MEV is going to go to zero. There's always going to be some amount of contention over shared state, but I think that ultimately MEV is going to go to zero as we build better and better mechanisms. We're learning so much, and this is kind of like a scary thing to admit because as everyone saw on Twitter, that like Base and a lot of like OP stack chains that rely on these priority fee ordering, that's how they make the most of their revenue. So I kind of think of it like, we need to eat ourselves and we need to like figure out new ways to make revenue. And this probably involves building applications that actually solve problems for users instead of just, making money off of like arbitrage and things like that. I'm really big into the idea of, it's time to build, it's time to ship like actual things that solve real problems for users. And the reason why I think that these debates are really important is like, I kind of, if an app takes off that's like too fast and it takes off and we have to like take a bunch of tech debt scaling at L2 just to like keep up with these apps, right? Like Base is like saying that they're trying to raise their gas limit, right? I see this as like taking on tech debt. And we can't, give up on decentralization too much. And there's going to be this constant desire to push the limits as an L2 and try to grow, and give up on some degree of decentralization. So what I want to see is L1 kind of figure out what the roadmap is and make it into like a big moonshot kind of plan. Like, this is how we want to move forward. And this is going to be like a huge, crazy project. And this is going to solve a ton of the problems. And then at L2, we'll be able to like adopt that, and it'll save us from, growing too fast and becoming, even more centralized than we are now.
So one reason why the ratio between congestion fees and contention fees is different between the L1 and Base is related to the fact that anytime Base has like meaningful congestion fees, they increase the gas limit. And they increase the gas limit every week or so. And so they haven't kind of allowed for real congestion fee market to develop and to reach some sort of equilibrium. And I think it makes sense, right? They want to try and grow as much as possible. They want to provide as low fees as possible to their users. And to Max's point, if they want to take this philosophy to the extreme, what they could do is like go back to first come first serve sequencing, and the advantage that would provide is that it would lead to more fees that are given to LPs, and ultimately like tighter spreads and better prices for users. And Base as a DeFi ecosystem would kind of grow a little bit faster if it were to actually go back to this first come first serve mechanism, which I believe it moved away from in July 2013 with the Bedrock update.
Well, I think the thing is you can have MEV taxes and you can get very similar or even better properties in a priority fee system. You're still going to have the issue of having the revenue go away, but it shouldn't be there in the first place, because the goal is actually to grow the pie in the long run, not to short-term extract value. If the goal was to short-term extract value, we should all start a trading firm and just do some MEV, right? But we're not doing that. We're trying to build and make Ethereum awesome. But I would say, like, right now, the current system where it's just like purely priority fee without MEV tax is more extractive, but it is also easier to make the jump from a centralized sequencer to a decentralized sequencer. And, it's very hard to have first come, first serve work well on a decentralized sequencer. And I think optimizing for having that jump be, a minor step up rather than a cliff would be a good idea.
So something that we've been thinking a lot about is actually running, if it would be a good thing for an L2 sequencer to run in a TEE where it commits to a particular block building strategy. And then applications can feel confident that they can, rely on priority fee ordering, for example, and do the whole MEV tax thing. Do you think that would be a good step forward?
Can I say these Ts do not provide censorship resistance, because you can actually like prevent, you can go outside the box and you can do message interception. So if you see a big opportunity, just cut off all the transactions going into your sequencer and put your own transaction in, and you can win the arbitrage that way. Even if it's first come first serve, you'll have like one transaction in the block or something. And if the opportunity is big enough, which they often are, often these opportunities are very long tailed. There's, once a day, there's a $100,000 opportunity or something like this. And it's not every block, there's $10 of opportunity. And so that's one of the issues with TEs, is that you don't get censorship resistance from them. You get a commitment to do a certain thing. Once it's inside the box, maybe they won't censor. But before it gets to the box, there's still control there, as long if you're decentralizing the sequencer to kind of prevent messages from coming in, and in some cases prevent all other messages, so you can win the auction yourself for free.
I mean, one of the things that I think the Flashbot team might be experimenting with, Suave, is to have multiple TEs. And so in some sense, the multi aspect, instead of being on the L1, it's on the L0, it's kind of off-chain.
But you need multi-proposer because you need to have multiple entities controlling what goes into their box, right? If it's the same proposer running the boxes, it's the same attack that I just said.
Potentially. What you could have is like the proposer kind of constrain itself with a TE, which says that it needs to get information from at least whatever K out of the N other TEs that are distributed.
I'm curious, Justin, if you have like a. I'm curious, Justin, if you have like just like an idea that you think would be better than for an L2 sequencer, that would be better than running a priority fee ordering in a TE.
I mean, the completely different direction that I'm a proponent of is this idea of using pre-confirmations. Basically, the idea is that the user communicates directly with the proposer, who gives them a cryptoeconomic commitment to include that transaction at a specific position. So if you're doing a Uniswap trade, you know immediately within one ping time of latency what is your execution price. And this kind of direct connection between the user and the proposer has some kind of wholesome aspects to it. One of them is that there's no more builders. And so like one of the vectors that we're kind of worried about is like this builder censorship, and instead you're kind of left with a direct auction with the searchers. So this was covered in the last pre-confirmation and sequencing call that is recorded. Another kind of nice wholesome aspect of pre-confirmation, well, of course it means that you can have a UX which is competitive with something like Solana, and even like more competitive than some of the L2s today that may have 2 second slot times. You go from 2 seconds to 100 milliseconds, so it's an order of magnitude improvement. But another kind of interesting thing is that it recreates this notion of a unified canonical mempool. So right now we have this very fragmented mempool. MetaMask has its own, proprietary mempool, and other entities have proprietary mempools, and that leads to power dynamics and exclusive order flow and opacity. And when you have pre-confirmations as a wallet, you only have one of two options. You can either provide the pre-confirmation, in which case you have to send the transaction to the proposer. You have no other choice, or you just don't provide pre-confirmations. But that might not be an option because the UX would be so much better. And so all the wallets would essentially be forced to send all their flow to this canonical place, which is the proposer. And so that reunifies the mempool. And then kind of another reason
Justin, sorry, can I just do you think that there will be separate lanes that each of the validators will create in order to maximize their revenue? Because there will be like fast and slow lanes, and they will
Right.
sell
So
that.
you do need a credible auction, and I guess this is where TEs can also come to play. I mean, you could use like fancy cryptography, but like the short-term solution is just to rely on trust. So for example, you can rely on relays that can play similar games, that can give priority to certain entities, but they're kind of trusted to not do so. The next level up is to upgrade it with TEs, and then the next level after that is basically to have threshold cryptography. But yeah, what I think might happen is that we move away from MEV-boost, where we have this notion of builders and relays, and then instead we have this kind of unified mempool, which is maintained by a so-called gateway. But like the
Sorry to keep interrupting you, Justin, but like none of this stuff actually solves the issue of the sequencer pricing different slow and fast lanes, right? They can intercept it on the NIC before it gets to the TE. It can be intercepted. The packets can be intercepted before.
I see. So this is where like the transparency comes in, and the wallets can do some amount of policing. So if I'm MetaMask, for example, and I know exactly when I sent the pre-confirmation request to the gateway, I might be collocated, or I might be X milliseconds away, and if I don't receive the pre-confirmation response X milliseconds plus some small delta, let's say 5 milliseconds, then I'm going to go complain to the operator of that gateway, or even more drastically, I'll just stop sending flow. And then what will happen is that this gateway would no longer be competitive because it would no longer be receiving flow from MetaMask. And what will happen is that the proposers would no longer use that gateway for their pre-confirmations. And so the system would kind of heal using market dynamics.
So one thing I'm kind of observing is we're kind of going into all the different strategies for kind of mitigating MEV and handling sequencing protocols. But like to Mark's point earlier, like kind of the time is kind of to get things in front of users, which seems to be somewhat at odds with like how fast can Ethereum evolve to be this layer for the L2s. So one thing I wanted to kind of hear, Mark, your take on, and maybe we can kind of turn this into a little bit of like an action item, like what should we do as a community in terms of next steps? It's like, how can we continue to iterate on these different approaches, but then ultimately not, end up in a situation where L2s are just completely floating away from the core of what Ethereum was supposed to be in the first place, which I think is a core part of Justin's argument. So maybe you want to touch on that, and then I'd love to hear also from Justin and Max, and maybe we can wrap after that.
Yeah, I mean, we're trying to make the OP stack be a very easy framework for people to experiment with things. Georgios and like the Reth team did a really good job with this idea of the AlphaNet, right? Like, I think that we should be driving our decision making with actual data by building prototypes and like running them, right? There's like a lot of back and forth about EOF, right? Should EOF go into Ethereum? Right, there should be like a live network with EOF running where we can observe the benefits like live, and then we can get hard data that in these numbers can like inform our decision making rather than just like talking about how it's good in theory. So I would see it being like a massive win if as a community we're able to do more prototyping and more testing of like potential improvements. And I would love to make the OP stack be like a framework for this so that we can spin up L2s. It's free software. Anyone can fork it and make any changes. We try to be as close to L1 as possible so that, L1 core devs can easily do it. And then we can learn a lot that way. On top of that, I want to see the kind of L1 community kind of come together. And I want to see the next kind of, Manhattan project of Ethereum. Like, I want to see something super ambitious, the way that E2 is like this big, ambitious game changer. I want to see something like that. I don't know if it's, ETH 3.0, I don't know what that means exactly, but everyone coming together towards something really ambitious and everyone unifying under that and just shipping it. That to me, I think is what we need to do as a community.
Justin?
Yeah, I agree with the sentiment that L2s are a perfect substrate for experimentation. And I kind of see this two-step process where step number one, like within these ecosystems, because there's a lot of trust and there's a lot of incentive alignment, we can try things that are collaborative. We can try shared sequences. We can just try, shared deposits or, shared provers or whatever it is. There's a lot of sharing opportunities. And then we'll have this period of time where we just learn best practices. But then I really want the community to think one step ahead in terms of having Ethereum-wide solutions. What can we do to have cross-ecosystem, collaboration? And I think that can only happen once we've had this period of experimentation. My personal thesis, as you know, is that for sequencing specifically, I think the L1, because it's like maximally credibly neutral, it doesn't introduce a new token, it doesn't introduce a new brand or a new security assumption. It is a place where Arbitrum and Base can feel comfortable, coming despite like working with their direct competitors. Now, all of this doesn't require any hard fork, and in some sense, like it's a Manhattan project at the standardization level, at the application level, and it's a social coordination game. In addition to being a hard technical challenge, because in order to get this synchronous composability, for example, you need real-time proving, which is the next level of SNOC proving, which is going to take time. Having said that, I think there also is an opportunity to improve the beacon chain, as you've alluded with Ethereum 3.0. I think, so the beacon chain was designed half a decade ago. And back then we had very little visibility on MEV and on all sorts of design directions like execution tickets, execution auctions. Only in hindsight did we realize that having 32 ETH validators was a really bad idea. Also, only in hindsight did we realize that not having stake capping was a really, really bad idea, and we need to have a smarter issuance curve. We want to snarkify the L1, the beacon chain. But for that, we need it to be SNOC friendly. And then, we chose the wrong hash functions and we designed our data structures to be not SNOC friendly. We also want the beacon chain to be post-quantum secure in some relatively small number of years. How are we going to do that? Well, now we have like all these legacy quantum insecure pieces of cryptography that are fairly deeply rooted into the beacon chain that kind of for which we need to pull out and replace the guts. And one of the observations that I have is that it is possible that the pace of governance that we have with this incremental approach, where we write an EIP, we go for the Oracle devs, and we have this hard fork every year or so, is just too slow to match the ambition of the L1 roadmap. And so I think, to your point, Mark, maybe there is some sort of an opportunity to have accelerated, some sort of clean slate approach where we accelerate the development through batching, where instead of doing 20 hard forks that's going to take 20 years, we do one hard fork which takes maybe 5 years, but we do it properly. And by doing so, we also have an opportunity to remove technical debt. And so, yeah, maybe there are like the beginnings of like a crazy kind of a new beacon chain, but it's something that we need to reach consensus on as a community.
Makes sense. Max?
I'm really optimistic about the future of Ethereum, no pun intended. But the thing I think we need more of is bandwidth between the 4 pillars of blockchain. You need engineering talent, obviously. You need economics / AGT type of stuff, which is where my focus has been. You need cryptography and you need distributed systems. And you need leading experts in all of those fields, which I think we have that part, but we don't have them talking to each other as much as I'd like to see. And I've been working on this braid paper with Alberto, who's a consensus expert at Miston, and Joaquim, who's a consensus expert at A16Z. And I've been working with Malesh, who's also a game theorist. And so we're kind of interfacing that, and the amount of learning that's come out of that and progress that's come out of that, I would like to see that between all 4 groups much more. That's one of the things that we're trying to build at Consensus Research at Special Mechanisms Group, is basically experts from all of those fields coming, working in the New York office, in the same office, working directly on problems that are like what I would say head of the chain problems. So like right at the forefront of what we need to do, part of that Manhattan Project. If anybody's listening to this and interested and fits those criteria, feel free to reach out to me on Twitter. My DMs are open. We'd be happy to hear from you. And I would say that's one of the things that we're trying to build for, is basically a Manhattan Project style lab of getting our Richard Feynman and our Einstein and all those people together, and in particular from different fields, and having them all work in the same office and just butt heads and go after the tough problems from like very deep, very specific level from day one, basically.
Sweet. Yeah, I love it. Manhattan Project for Ethereum. I think we're going to need it. I think we're entering into a period where, Ethereum is really starting to get more adoption, and it's only going to get more important year after year. So, I hope we can see more of this stuff get adopted. But cool. I think we're just running short of time. I think we could have kept going for much longer. There's still tons of stuff we could untease, but given the time constraints, I want to say thanks, guys. It's been a really awesome discussion. Appreciate you taking the time, and thanks also ETH Global for hosting.
Thank you, guys. Kartik, you're muted.
That was awkward. I did a whole speech thanking you, and nobody heard it. But I want to say, well, thank you, Mark, Max, and Justin, for this amazing discussion. There's a lot of cool stuff here, and I think the part that I took away was that there are very interesting sort of sides on kind of all of from your perspectives, and it's fundamentally still about trade-offs and kind of thinking about what is that we're optimizing for the end user. And our part is there's so many different categories of who those users are and who those builders are. So it's going to be something that we're going to still continue discussing in the future, and I'm looking forward to having all of you come back sometime and continue this conversation. So thank you, and thank you, Liam, for moderating. All right. Well, this was our last talk for this summit. 20 to 48 hours before all the projects are due. So I want to wish all of you happy hacking and all the best with submitting your projects on Sunday. We're looking forward to seeing hundreds of projects coming out of ETHOnline. So can't wait to see what everybody builds. And next Friday will be the finale where we're going to show you all the best projects. So thanks, everybody. Happy hacking. And in the meantime, enjoy some lo-fi beats. Take care, everybody, and all the best.